Welcome back, everybody. In this exciting episode, we're finally going to get to do some work. So I know that you're disappointed to learn that all the homework that you've been doing and things didn't actually involve any work. But, from a physics perspective or definition, we actually haven't been doing work. We've just been working. So the physics definition of work, you probably remember from high school physics somewhere, is that work is force times distance. Now, that's assuming two things: that the force is constant as we move an object from one place to another, and that the force is operating in the same direction or the opposite direction as we're moving the object. So, for example, suppose you have a 2-pound book and you move it up 5 feet. Okay, then according to this, the work would be 2 pounds times 5 feet, which would be 10 foot-pounds of work. So a couple of quick comments. Number one, notice that I said we had to move the book up 5 feet. So that's because the force on our book is the force that comes from gravity. So the force is pointing down, right? By moving the book up in the opposite direction of gravity, then we actually are doing some work. So the physicist would tell you, if you take your book and you move it horizontally, from Lubbock to Amarillo, and you move it horizontally, never up and down, then you actually don't do any work because you're not moving your book in the same or the opposite direction as the force being applied to it. So I always want to say at that point to some physicists, yeah, you come lug a book around all day, moving it side to side and see what you think you haven't done any work or not. But the second quick thing to mention is you may have noticed that I'm using English units of measurements, pounds and feet and so forth. The reason is I'm a mathematician and I can use whatever units I like. So I think in pounds and feet and miles and this sort of stuff, not in newtons and meters and such like. So for most of the examples we're going to be doing, and you'll see this in the textbook and on the exam, we're going to be using, foot pounds. We'll be using feet for distances and so on. There'll be some examples in the homework that will use metric units, and of course some that use English units too. Metric units, sometimes we'll call this is scientific measurement. So I'll put on my mathematician hat for 5 seconds. There's nothing inherently scientific about using newtons or meters or joules. It's just that these are the units that most scientists use, not that it's especially scientific. So the math is all the same, whether you measure your units in foot pounds or in newton meters, it's all the same thing mathematically. So in metric units, if we were using force in newtons and our distance in meters, then we get newton meters for the units of work, which we would more commonly call a joule. Now, in the homework, you'll notice that there are some problems using very small forces and very small distances, in which case we would measure the force in dynes and the distance in centimeters, and a dyne centimeter is also called an erg, which I find absolutely hilarious because whenever I see erg, I'm just imagining some poor zombie trying to do work, walking around going erg. So, anyway, so here's an example. Let's say that we have a force on a particle which is given by x squared newtons. So I'll break down and do a newton example, but almost all the other examples will be in pounds. So the force is given by x squared newtons, where x, of course, is the position of the particle. So for example, if our particle is sitting at the origin, and when x is 0, then the force on it is 0 squared, and so there's no force. It doesn't have any force on it at all. If we move the particle over to, say, x equal to 3, then the force on it would be 3 squared, which is 9. So the deal is the force is changing as we move the particle around. Right? The question is, how much work does it take to move it from x equals 0 all the way over to x equals 5? Well, this is the reason this is in the textbook, and the reason every textbook does this sort of thing as an example is really just to remind us of the big idea we've talked about from the beginning. That is all about integration and what integration really means. So if you remember back when we talked about this the first time, something was changing. right? In Calculus 1, that was the height of a graph, right? Since we've had lots of other examples of something changing, it kept us from using the old algebra formulas. So in this case, we're not going to be able to use work is equal to force times distance because the force is changing as we go from one place to another. So what we do is we break the problem up into pieces and we pretend that what was changing isn't. So that in this case, that would be our force we'll pretend is constant on each of the little pieces of distance that we use. We find the work on each piece using the old formula because we can now use the old formula since we're pretending that the force is constant. Add up all those pieces, well, that's a Riemann sum. If you use more and more pieces, let them get smaller and smaller and smaller, that's the definition of a definite integral. So the answer will be a definite integral. And more importantly, it'll be the right answer because, pretending that things were constant on each piece gave us, well, an answer, but it was wrong, right? It was kind of close, but it wasn't what we were looking for. But if we use more and more pieces and we set everything up correctly, then what we get will be an integral, and more importantly, it'll be the right answer to the question because we've set things up to make it be that way. So back to our example. We have a particle. The force on the particle is x squared newtons. We're going to move it from x equals 0 to 5. So what we do is we take this interval from 0 to 5, we split it up into lots of small pieces. So we'll break this up into pieces here on our screen. Okay? And what we'll do is pretend that the force is constant on each of those little pieces. So how big is each piece? Well, it's delta x long, right? So the distance that a particle will move from one piece to the next, it'll travel delta x. Our distance is delta x. Our force is f of x. And so if we add up f of x times delta x on each of those pieces, that's our Riemann sum. As we use smaller and smaller pieces and more of them, of course, the Riemann sum turns into an integral. So we'll have the integral of x squared, that's our force, times not delta x, but in the integral that becomes dx. And we'll integrate from 0 to 5 because we start when x is 0 and we stop when x gets all the way up to 5. And if you actually go through and do the algebra, which I'm not going to bore you with doing, you end up integrating this and getting like 125 over 3 for the answer. Okay, so every book, as soon as they do work and they do these sorts of problems, they immediately jump over and talk about springs. And that brings us to Hooke's law. So the reason for doing this is because springs are an easy example of something where the force is changing. We don't have to make up something like, say, a particle is moving in some weird force field that I just made up. Everybody's familiar with springs, and the rule about how springs works is not that complicated to understand. It's Hooke's law. It says that the force on a spring is proportional to the displacement. So that means that the force, f of x, is some constant times the displacement, x. All right, so we need to pause for a second to explain what all these letters mean. Because the K is a constant. That depends on the spring. So if we're talking about a slinky, right, then the K will be really, really small because a slinky doesn't exert a whole lot of force when you stretch it back and forth. If we're talking about some ginormous industrial strength shock absorber, then the K will be huge. The X in blue there is our displacement. That's not the position of the spring like we had in the last example. It's not about where the spring is. It's about how far the spring has been stretched. So of course, if you have a spring and it's not stretched at all, then there's no force on it because it's just laying there and hasn't been stretched. But the more we stretch it, the more we displace the end of it, then the bigger the force will be because that will make x larger and larger and larger. So remember, our force is some constant times the displacement. Maybe another word for displacement, if you don't like that, is the how far it's been stretched. Okay. So here's an example. In fact, this is a two-part example because books love to do these sort of two-part example problems. So spring is normally 5 feet long. Okay? It's a big spring, big 5-foot long spring, but it's not a really stretchy spring or not a very stiff spring because a 4-pound force, which is not very much, stretched it another half foot. So as soon as somebody put a 4-pound force on it, it was enough to stretch it from being 5 feet to being 5.5 feet. Okay, so first part of this problem, first step in almost all these kinds of problems that you'll see in the homework and in every other textbook. Find the K, find this constant. So remember that Hooke's law says the force that a spring generates, right, is equal to the constant K times the displacement. Well, the force in this example was 4 pounds. The displacement was half a foot because it was stretched half a foot. So 4 is equal to K times a half, multiply both sides by 2, and you get that K has to be 8. So that's very, very typical part one. After you've done a bunch of these problems, you'll be like, yes, 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 they all work the same way. The typical thing is to tell you enough information to find the K in the first part. And the second part to ask you to find the work or find force or find something else. So here's another typical part two. Right? How much work does it do to stretch this spring from being 6 feet to being 8 feet long? Now, the tricky thing here, right? The big flashing letters, important. Look out, this is an easy place to make a mistake, right? In this case, the 6 and the 8 aren't the critical numbers, right? 6 feet and 8 feet are how long the spring is. But what I really need to know in order to work the problem is not how long the spring is. I need to know the displacement, how much it's been stretched. So in this case, the stretchiness, as my displacement stretches out there, it has been stretched from 1 foot to 3 feet. In other words, from going from 6 to 8, right, means 6 foot long to 8 foot long, right, means that it has been displaced from its normal length of 5 feet, right, to going from 1 foot of displacement to 3 feet of displacement, right? Because if I'm at 6 feet long and I'm normally 5 foot long, that means I've already been stretched 1 foot. By the time I get to 8 feet and I'm normally 5, that means somebody has stretched me so that I am displaced 3 feet from what I normally would be. That makes sense? So I'm really stretching it from being 1 foot longer than normal to being 3 foot longer than normal. That's the way you think about this. So the work, of course, will be the integral from 1 to 3 of the force. And we figured out the K in the first part of the problem. That was 8. So our answer is the integral from 1 to 3 of 8x dx. Of course, if we're just setting up the integral, that's good enough. If we're trying to find an answer, we could integrate that pretty easily. And we get a number that's like 32 foot-pounds. Notice that the answer will be in foot-pounds because we're measuring distances in feet and our force was being measured in pounds. So here's one more quick example. I put this one here because there are homework problems that look like this, and it's sort of the flip side of the one we just did. So this says you have a 3 foot long spring and it's been stretched until it's 5 feet long. But when you did that, it took 50 foot-pounds of work. So this is sort of the opposite way of trying to find K. Instead of giving you a force, I've given you an amount of work. So this is a little trickier, and so I thought maybe we should do an example like this. So 3 foot long spring, been stretched until it's 5 feet long. So first thing to ask yourself is, what's the displacement? Because the 3 and the 5 aren't the important numbers, right? It's that it's been stretched, well, from 0 to 2. Why? Because it's 3 foot long to begin with, and we stretched it till it was 5. So it started out 3 feet long. That's how long it normally is. And so it was originally displaced nothing. It was 3 feet long spring, and it was 3 feet long when I found it. Then I stretched it until it was 5 feet long, which means I stretched it 2 more feet. So the displacement went from 0, not stretched at all, to 2 feet, okay, where it had been stretched until its length was now 5. Makes sense? The important numbers aren't the 3 and the 5. The important numbers are the 0 and the 2. Okay, the force on the spring is K times X. Now I don't know the K, right, but I do know that the force will be K times X. So I can write down an equation that says, K times X is my force, and I'm going to integrate that from 0 to 2, and I should get 50 because that was the amount of work it took to stretch it from 0 feet of displacement to 2 feet of displacement. Now, this looks a little weird because this is a more complicated kind of equation than the one we wrote down a few minutes ago, where they gave us the force and we solved for K pretty quickly. This will take a couple of steps because now what we have is an equation with an integral in it. But the cool thing about this is, notice that we're integrating with respect to x, not k, And the k is just a constant. It's just sitting in there like a constant. So if I integrate x dx, then I'll get 1 half x squared. And that constant that's in there for k just comes along with it. So the left-hand side there becomes 1 half k x squared. And I evaluate this between 0 and 2. And then whatever I get there on the left-hand side, that should still equal 50 foot-pounds of work, because that's what the problem told us the work was. Now I plug in the 2, I plug in the 0, do some algebra and subtract. The 2 squared, of course, becomes 4, and there's a half there for it to cancel with, so it gives me 2k, and of course the 0 just gives me 0. So that whole left-hand side becomes 2k equals 50, and so of course k has to be 25. So this is a little bit harder problem because we've had to find the k given work, right? But this is very, very, very common of what you'll see in the homework. Almost all the questions that show up in every book about this are, number one, find k, and number two, use the k to find something else. And so how do you find the k? Well, they either give you a force and you use the force is equal to kx equation, or they give you a work and you use the fact that the integral of kx is equal to the work. That lets you find the k. And then once you know k, they'll either ask you about work doing something different or force doing something different. It's a very, very standard sort of thing. In some ways, all these problems are a little fakey, right? Because these problems are not, well, okay, so textbooks will claim these are, quote, real world problems, quote. But I mean, how often have you ever measured a work done on a spring to stretch something? Unless you're a spring engineer, this is not something you do all that often. So why do we do this? The real reason is this big idea, right? This is another example over and over and over again of seeing what happens in some sort of a word problem where we can use integration, and understanding how we can break things into pieces and use an integral to solve the problem. That's the key skill here, right? Solving silly little problems about k's and springs, well, that'll be important for the exam, but it's not, and the homework, but it's not the end all and be all of the skill you should get from this class. The big skill you should get from this class is the ability to recognize when something's changing so that you can break things up into pieces and use an integral to get the answer.